Hello students. So in a previous lecture we have discussed about the various power stages involved in an induction machine. We've seen how what are the various losses that are occurring. Suppose if you talk about stator losses and rotor losses, so what are the various losses that are occurring in an induction machine? Okay. So in today's lecture, what are we going to do is that we'll we'll derive the expressions for this power, and you can come directly to this slide. So we will derive the expression what actually the power is. Now we know that this motor power input is, as I've already told you, is root 3 into V into I1 cos phi. See here, over here. I've already told you this root 3 V I into this is the input to the stator body, input power to the stator body. Now you should know one very important thing is that that power is equal to torque into omega. Okay, this formula is very important. Active power is equals to torque into omega. You should be very careful about using these formula. Why? Because you, and one more important thing, that you should be very careful about the units of the various expressions involved in this power, parameters involved in this formula. Like the unit of power in this formula is always watt. I mean, it is in watt, and then the unit of torque is Newton meter, and obviously the unit of omega. Omega is what? Synchronous speed, your speed. So the unit of omega, whatever speed, not only synchronous speed, whatever speed. So your unit of omega is radian per second. Now we also know that this omega is also represented in terms of your rotation per second or rotation per minute. So what is the formula for doing that? We know that omega is equal to nothing but 2 pi ns. Okay, 2 pi ns, where 2 pi small ns, where small ns represents the speed in rotation per second. This thing is very important. We have already discussed this thing in during your class lectures. I've already told you how to convert omega into radian per second into rotation per second, or radian per second into rotation per minute. Now we know that omega is equals to 2 pi small ns. Small ns is in rotation per second. Now we know we want to calculate in rotation per minute. Then you can obviously divide it by multiply that thing by 60. So you can also write omega is equals to 2 pi capital ns divided by 60, where capital ns is nothing but your speed in rotation per minute. Okay, so if you want to convert radian per second into rotation per minute, then you'll use the formula omega equals to 2 pi n divided by 60, where n is in rotation per minute. And if you want to convert your radian per second into rotation per second, then you'll directly use the formula omega equals to 2 pi small ns, where small ns is in rotation per second. See, this thing is very important, and you must be very careful about using these things. Okay, because if you, in place of speed, in place of omega, if you replace it by ns and then capital ns, that is rotation per minute, and you are not dividing it by 60, then you will get a complete wrong answer, because omega is replaced by 2 pi small ns, that is rotation per second. If you want to replace it by capital ns, then you need to divide it by 60. Now we know that the formula for power is P equals to torque into omega. So now this thing, you can see that rotor power input, this is power, is equals to nothing but torque. So this is torque into omega. Now omega is written as 2 pi ns divided by 60. Now this is capital Ns. So this is in rotation per minute. If in place of this rotation per minute, if we have speed in rotation per second, then we'll directly replace it by 2 pi small ns, that is a rotation per second. No need of dividing it by 60. Okay, these things you should be very careful about while doing your numericals. Okay, otherwise whole calculations will be you'll do wrong calculations. Okay, so this is rotor power input equals to 2 pi ns divided by 60 into tg. Okay, okay, now this is rotor power input. Now what do you mean by rotor power input? As I've already told you, rotor power input is nothing but your PAG, air gap power. Whatever power is there comes from the stator to the air gap, goes to directly to the rotor. So PAG, your air gap power, is nothing but your rotor power input. That's why you have taken this speed as ns. This is synchronous speed of the field, that is the speed that is involved in the air gap. You are having basically ns speed. Now what is the power of rotor power output if you want to calculate? What is the output power of the rotor? Output power of the rotor, again the same formula, torque into omega. Now torque is the same electromagnetic torque that is developed into omega. You can replace it by 2 pi n divided by 60. Now in this case we are not using ns. Instead we are using n. This n is again in rotation per minute, but this n is your rotor speed. This is not your synchronous speed. This is your rotor speed, n. Okay, be careful. You are taking this rotor speed? Because this is your rotor power output, and here you are taking ns because this is your rotor power input. This is your air gap power, and in the air gap this power is encountering the field which is rotating at ns. And this rotor power, when you are talking about rotor power, then this is encountering the field, this is encountering the field which is rotating at means n. The rotor is rotating, since the rotor is rotating at n speed, that is why you are using this formula. So whatever power you want to calculate, you just have to correlate what is the torque at that portion and what is the speed of that particular thing. Then you can multiply the torque into speed, that will give you the power straight away. So this thing is very important. That's why I made star over these things, that this is very important, when to use this ns and when to use this n. Okay, if we talk about air gap power, then always use this ns. If we talk about rotor power, then use rotor speed. Air gap power, then use air gap speed. Now if you talk about what is the motor output or shaft output, see, I'll show you again this thing. This is your air gap power, this is your air gap speed. That is why you were using ns for calculating that power. This is your rotor power. Now yeah, now here you are using this rotor speed. The shaft speed and rotor speed both are same. Now when you need to calculate the shaft power available at this shaft, then you will take this torque, shaft torque, and speed will be this. Why? Because the speed of the shaft and rotor are same, one and the same thing, because the rotor is directly attached to the shaft. So the shaft is also rotating at the speed of the rotor. So again, now you're calculating here, you're calculating this motor output or shaft output. If you calculate shaft output, then you will take shaft torque and the speed of the rotor, or this is also the speed of the shaft. Okay, now we know that this gross torque that is developed minus the shaft torque is nothing but the torque loss due to mechanical loss. As I've already discussed in this diagram, that this torque here the torque developed was Tg, and out of this some loss is there, some torque is lost in mechanically while rotating the shaft, and hence that is known as torque lost in mechanical loss, and thereafter you finally got this T shaft. Okay, so you should be very careful about these things. There's a few expressions. Now after this thing, you can say that the rotor power input minus rotor power output. If you calculate the rotor power input minus the rotor power output, is nothing but we are using the formula 2 pi ns tg by 60 minus 2 pi n tg divided by 60. So this rotor power input minus rotor power output is nothing but rotor copper loss. Means whatever rotor power input is there, if we subtract rotor copper loss from them, we'll get rotor power output. So rotor power input minus rotor power output will give you rotor copper loss, and the value of the rotor copper loss will be this thing. And here ns minus n can be replaced by sns. So you can say this s times, you can say this is nothing but s times rotor power input. Why? Because the formula for rotor power input is what? 2 pi ns tg divided by 60, and the formula for rotor copper loss is s times 2 pi ns tg divided by 60, same thing. So rotor copper loss is nothing but s times rotor power input. This thing should be very careful, and this is very important. And this rotor power input is nothing, we denote it by PAG, air gap power, as we have already discussed in the previous video lecture. This is air gap power, PAG. So rotor copper loss, so copper loss in the rotor is equal to slip time air gap power, not the rotor power input, one and the same thing, because air gap power is equal to rotor power input. So rotor copper loss is equals to slip times rotor power input. Now again we can find out rotor power input is equals to rotor copper loss divided by slip. You can just manipulate things. After this thing, we'll skip few of the slides because these slides are not important for you. So you also skip these things directly, because these are not asked in your syllabus. We'll directly go from here. We'll directly go to this thing. We'll directly go to this power flow diagram. Now what does this power flow diagram signifies? Again, the brief, whatever we have discussed till now, I have put it in this diagram briefly, that this is the input power, that is entering into the stator. Then there is stator copper loss and stator core loss both. Core loss, sometimes they also neglect the core loss of stator also, but then sometimes they do consider it also. So you can take it, if they are mentioning the core loss is also available, you can take it, or otherwise you can also subtract these things. So this is the stator copper loss that is being subtracted. Then you will get this thing, the air gap power from P input. When input power, when you subtract stator losses, you get the air gap power. From this air gap power, when you subtract the rotor copper loss, you get the gross mechanical power developed. Now this, actually they are not taking, in this diagram we are not taking considering the mechanical loss. We are assuming that the mechanical loss involved is zero. So that's why the after, when we subtract this rotor copper loss from PAG, then we directly get the gross power output, that is the shaft power output directly. So but now one thing, we know that the PAG is nothing but air gap power, and as we have discussed in the previous video lecture, that PAG is nothing but thrice of I2 dash ka whole square into R2 dash by S. See, I'll show you again. See, in that equivalent circuit that we developed, Thevenin's equivalent circuit, in that I've shown you that this thing PAG is nothing but I2 dash ka whole square into R2 dash divided by S. So this is very important, and this expression of I2 dash, this is also we are going to use. How we are getting this I2 dash? By this circuit VTH. So you need to remember this circuit very carefully, because this is what is being used everywhere from now onwards. Okay, this circuit needs to be means you should go through this again and again. Okay, this circuit needs to be understood very carefully. Okay, so this is PAG. PAG is what? I2 dash ka whole square into R2 dash divided by S. That is what we are using. Again, we'll come back to that thing. Yeah, here. So this PAG is equals to nothing but thrice of I2 dash ka whole square into R2 dash divided by S. Now we know one thing, this, as I've told you earlier also, that thrice of R2 dash ka whole square into R2 dash divided by I2 dash ka whole square into R2 dash divided by S. This expression consists of both power loss in active power loss in rotor ohmic, in rotor resistance, as well as the active power loss or active power consumed for mechanical energy, for mechanically rotating the shaft. So this power include both these things. So what is the active power lost in rotor, on the rotor circuit? If we want to calculate, then we can directly find it out. What it is? It is thrice of I2 dash ka whole square into R2 dash. This thing, thrice of I2 dash ka whole square into R2 dash is nothing but your rotor ohmic loss, the copper loss in rotor. When we are dividing it by S, then basically it consists of both ohmic loss plus this mechanical. But this expression, thrice of I2 dash into R2 dash, this upper expression, this basically denotes your rotor loss. See, okay, this rotor law. So if we multiply this slip, if we take this slip away and we multiply this slip this side, so S times PAG is nothing but thrice of I2 dash ka whole square into R2 dash. S times PAG is nothing but thrice of I2 dash ka whole square into R2 dash. And this thing, this side, right hand side, we know that this is not, this is equal to your rotor copper loss. So this is the expression. S times PAG is equals to rotor copper loss. This is what we have developed previously also here. See, directly. This expression we developed here also. Yeah, see this. Rotor copper loss is equals to S times rotor power input, or S times PAG. Since rotor power input is equals to PAG. This is what again we have developed here in this thing. Okay. Now one thing more. So this is S times PAG is rotor copper loss. So now what is this gross power developed in terms of slip? If we talk about what is the gross power developed in terms of slip, then see this is PAG minus rotor copper loss. Now what is rotor copper loss? Rotor copper loss is thrice of I2 dash whole square into R2 dash, which is also equal to S times PAG. So if we subtract this S times PAG from PAG, then we'll get this gross mechanical power output. So this is nothing equal to PAG minus S times PAG. So we can also write this is equal to PAG into 1 minus S times. So gross mechanical power is equals to 1 minus S times PAG. So one thing you can see from this power diagram, that once you know this thing, PAG, then you also know the rotor copper loss. You know PAG, and if you know the slip, then you can directly, if you somebody is asking how much ohmic loss or how much loss is occurring, active power loss is occurring in rotor resistance, then you can directly find it out, like this much loss is occurring. What? slips times your PAG. If you know this PAG, just multiply it with these slips. This much loss is occurring in rotor copper loss. Okay, then if they are asking you how much mechanical power exactly, gross mechanical power is developed across this shaft, then you can directly find it out by this PAG. When you multiply it with 1 minus S, then this will give you this gross mechanical power output. So this expression is very important. S, rotor copper loss is equals to S times PAG, and rotor gross mechanical power developed by the rotor is equals to PAG into 1 minus S. And what is PAG? PAG is your air gap power, which we obtain by when we subtract this stator loss from the input power supplied to the stator through the source. So this is the complete power diagram. You need to go through it again and again, so that you will be more familiar with these things. See, again, now this NR we will, okay, we will discuss further in your next lecture, but I'll again request you, I'll recommend you to go through this power flow diagram again and again, so that you'll be able to get into a more clear picture in your next lecture. Okay, thank you very much.